Okay, hello everybody. My name is Boguslaw Cyganek, and the talk will be about computers and computations, as you see the title. And I came from AGH University in Poland, so we do a lot of computations, but we also use C++, teach C++. We also cooperate with companies in machine learning, artificial intelligence. So this talk will be about computations, and also with, I hope, a lot of practical things you can take on with you, how to make computations faster and data smaller or compressed. So the idea is, the plan is here, so I will start with what we already know about the already 40 years old standard in floating point computations, but quite fast. It is not about the old standard. It is more about new approaches, new standards, or future standards. So the quest for shorter formats, and then I will mention about some cool libraries to compress floating point data, which you can use in your production code. And new kid on the block is POSIT, arithmetic. There are many new approaches to make this floating point computation representations more useful. So one of them is POSIT. I don't know if this is the future standard, but we'll see. And also, we'll see some libraries, C++ to use POSIT. And then we'll see some new directions, quite new cool stuff from just last month in reinforcement learning, how probably some algorithms will be developed in the future with help of artificial intelligence and reinforcement learning. So as I mentioned, this is me and Prometheus computer at our computer center. Just in the period of something like 20 years, we see the still growth of computational power of computers. This is Prometheus in top 500 computers. We try to keep it on the list. But if you observe this memory line, it is also growing, but not that fast. So what does it mean? It means that data transfer is a bottleneck at large processing scale. And we live in the area of big data. We say in university, data is the king. Yes? So whoever has data can do whatever they want. So time is quite specific now. So every bit counts. So what can we do? So mostly these parts of my talk will be about how to compress or how to use different formats and save on data and transfers. So, well, starting from very basic level, what we teach on the first meeting of C++ classes is how to use some values. And the fast thing is just start with some examples in computations. So usually students start with some sliders, that they write some code, and they are surprised what is going on here. And the fast solution, instead of explaining what's going on here, is just to take doubles and we are done. So we go quite easily from integer computations to floating point, and we are done, okay? So in some cases that's okay, but if we are processing, for example, images, video, and we do some computations, you know about convolutional neural networks, we do a lot of computations on pixels. So going from 8-bit pixel or RGB, 3 bytes, to 3 times 8 bytes of doubles is just pure waste of space, time, and energy. So what we can do more. But before we go to this part, what we can do, let us take a look at what we have right now. So we have this IEEE 754 standard. If you wish to see some more basic things, I was talking about on a few conferences, also here, but here is the previous talk, only about this the standard and some pitfalls. We need to refresh from time to time what we are doing. Also, you can find some material in this book for beginners and intermediate students. I published this with Wiley a year ago. So there is an entire chapter 7 about computations in fixed point and floating point. But let's start with some history. So once upon a time in a galaxy, there was no floating point standard. So what people did at this time? So computers use many different representations of floating point numbers, and the lack of floating point standard was really a hard problem in 70s and up to 80s because, well, you could not move the code from one computer to the other computer and have the same results with the same code. Well, like usually in such cases, major companies, they had their own standards like HP or IBM. So, but it was a problem. So this floating point compatibility was in desperate need of standardization. And indeed, we had it. So we have this seminal paper by Professor Kahan, Walter Kahan, why do we need a floating point arithmetic standard? And you see this is more than 40 years ago. Well, just citing his words, like numerical software is costly and most programs must be portable over diverse machines. And we need something simple, not so capriciously complex, and he mentioned that he devised this standard, and the standard is what we need, but he ends his paper, alas, the proposed standard will not guarantee correct results from all numerical programs, but the standard weights the odds more in our favor. So he was aware that the standard is not maybe perfect or just optimal, but this is what at that time people came to. And here is what we all know from the school is just we'll need this picture again when we will be talking about POSIT, so therefore I put it here. So just going briefly, the standard defines many formats. We will return to this formula again. So we have single precision, double precision. So single precision format occupies 4 bytes, and we have this precision 24 and 8 bits for exponent. It usually is encoded in our languages like float. And in C++, we have double, which means double precision. In this IEEE standard, 8 bytes and 53 bits of precision and 11 bits of exponent. Extension that precision, which some compilers implement like long double or even quadruple precision with 16 bytes. Also sometimes implemented like long double, but this is machine specific. If one or the second is long double, or even the standard only says that it should is at least as precise. So float and long double as double respectively. So the standard says that the longer precision representation is not worse than the previous one. But it appears that in many computations it is a waste, actually, going higher and higher. This was for 40 years. We were just trying to make computers wider, buses and have more bits in the computer world. So we came from 16 bits to 32 bits, computer 64 bits, maybe 120, and so on. But at some point, we had to stop and reflect what we are doing. And in many, many cases, like with the slider, even the computations can be done on bytes. And in many cases, like deep neural networks with millions of parameters, we need floating point computations, but 16 bits is enough. So we have this way back to 16-point standard, just introduced in 2008. So we'll see in a moment what possibilities we have as programmers. So returning back to the basic formulas of this standard. So if we have number of precision bits and q bits of exponent, the value of this floating point representation is like this. We see that this is sign magnitude representation to some extent because sign is separate. We also see that with this representation we will have two zeros, -0 and +0, which is also waste, and we'll see more such gaps in the space of values in a moment. And also M is unsigned significant called mantissa or fraction. B stands for a base and E denotes the exponent. And this exponent is biased, so it can be negative and positive, but the value will be always here encoded like positive value. And for P digits and B base, a value of significant is given by this formula. So we see that last position weight is this depending on dp -1. And we have also this d0 value here, which is specific. And if we make a closer look at this representation, we'll see that a representation of numbers is not unique. So if we don't constrain a couple of things here, there will be many representations of the same value. So the committee decided to normalize form. So they decided that the 0 will be always not 0, this first bit. And this way, we have so-called normalized value. And because the base is 2, so we have only one choice of 1 in this case, so we don't need to store this bit anymore. So we assume that the 0 is always 1. And this is called the hidden bit trick, just not storing this bit. We'll see in a moment. And but with this representation, if we go back with the formula and we set this bit always for 1, so we have immediate problem. We cannot represent the 0 quite easily. Yeah? So we have to wait. If we have normalized form and just unique representations, or we have some problems around 0. And really in IEEE standard, we have problems near 0. So we have special encoding called the normalize, which in practice on some platforms means that computations of a really tiny value is really slow. And as I mentioned, this exponent is biased, so it is shifted. So it is always positive in representation. So the best thing to grasp the idea is just to make a simple experiment. So let's make very short floating point representation with all this information I provided. So we have this formula again for convenience. And let's assume we have only 3 bits of precision. The base is again 2, and we have only exponent in the range of -1, 0, 1, and 2. So if we draw such a what values can be represented with such a tiny representation, we see very specific groups of values for each exponent. Floating point values are shown in red. So what is obvious from this picture? We have no representation except 0. We have no values near 0. Quite surprised. For each exponent, okay, we have 4 groups for each exponent, and then they tend to gather together. But once we go from a group to another group, the spacing is larger and larger. And look at this. We need to represent real values, and actually, we have only a couple of points which are precise. Everything else, what is on this horizontal axis, will be approximation. So that's, well, for us it is obvious. We take double, we do some computations, but actually, we are doing only approximations of real values. So it has consequences. So spacing within a group is the same, but going from a group to a group, it increases by a factor of the base. So this is another debate what the base should be. You will see some approaches in POSIT values. Okay, so you see if you go here, the spacing is growing up and up. So you will see that the quantization error will be bigger for bigger values, for bigger exponent. And the conclusion is that in floating point, real values cannot be exactly represented. So due to Randolph errors, the associative principle doesn't hold. So the order of operations matter, which is not in mathematics. So summation, for example, or multiplication is associative, commutative, associative, but not in general in this domain of our computation. So we are doing computations every day, and we have to deal with this. And you will see, well, in my previous talk, you can see that if we, for example, adding values from very small to very large, if you sort the values, should it change the result? Well, theoretically, no. But in practice, if you start from a wrong value to large and you go to the smaller ones, you will lose the value. So the order matters. Just make such an experiment. Generate some values from the small one to the big one, and then sum them up with accumulate, for example, and then sort them and sum them up. And the second surprise can be in concurrent world of power programming. You split your matrix into parts, you sum the values, and always you will have different results. Why? Because there is a preemptive mechanism changing the order of summation, and, well, so you have to understand this and see if you have problems with some synchronization in your code, or this is just this phenomena of adding the values. And we have some special values, positive, infinity, negative, negative 0, positive 0, and so on. We have special representation for not a number. All exponent values of ones are used to represent special something. For example, you compute square root from negative value, you will obtain not a number. But this is the waste of time. Here we have space for improvement because the standard says, okay, exponent values are ones, but we have only 8 exponent values. What with the rest? The rest is wasted in the old standard. So the other standards just use this gap. Well, yeah, encoding with value of double precision. Yes, I already mentioned that this is biased. And the special computations are for the normals. So there is a special encoding for values zeros. Well, obviously, we have positive, negative 0, which is no good. But for tiny computations, we enter the other world of the normals. So the algorithms are changed a little bit, and we compute with different representations, and I found code in DSP, digital signal processors, for example, when people just trying to avoid this space because it was really slow in computation because there are different algorithms. They added 0.5, did computations with larger values, and then moved back with the result. So this has some consequences as well. And naturally, we have roundings because of these gaps between the values. Well, you know this default is round to nearest, but we have also optional round to nearest ties away from 0, round toward infinity, to the larger value, round down, and also round toward 0, so cut off fractionals. And actually, this is why the first line of code I showed you didn't work, because well, if we divide integers, we have still integer, or just if we have we convert double to integer, it will have the fractional cutoff. And some short examples of representation. So you see, this is biased by 127. So, for example, -1, how to represent. And we have this hidden bit. You see, we don't store it here, the 1. So if we put into the formula, we have -1, just a minimal value, because I will mention in a moment minimal value. So minimal is all zeros, and exponent is 1. So we have something like this. Again, hidden bit is just added externally because it is always 1, this D0. But we can also read it out for float. I will mention in a moment this numeric limits and numeric libraries we have in C++. And also, what is the maximum value? We have 254 here, and because all ones are reserved for special representation, so we have this value. Actually, this is not reciprocal of minimum. So if you multiply minimum by maximum, it won't give you 1, surprisingly. And we can read it out for float, or for double, or for other values. And, well, you can play with this. You can find a lot of calculators, or you can ask your students to write. If you're teaching, this is good exercise, how to convert to these bits, and play with that. OK. So I'm just finishing with the standard. So again, what is the, well, we have round-off errors. We need to remember about lack of associative law. Order of operations matters, actually. And, well, when we are doing computations, we need to remember about special value, which is called machine epsilon. It conveys a value represented by the lowest bit of the significand. And actually, it is, because we don't have this close to 0 representation, this is from 1 to the next when you change the least significant bit. So this is the distance. This is epsilon. It plays the important role. I will mention in a moment. OK, so, and, well, it can be used to assess the threshold when you are doing computations. And we have to remember that adding values with different exponent leads to large errors, and also subtracting close values can lead to severe cancellation errors. So if you are subtracting very similar values. Why? This is in another talk. So I will just put some well, recipes for you, and we finish with the standard. So what we do in computations, in math, we are doing iterations, and we are checking if the algorithm is converging to a value. So we are checking if the new value is different from the previous value. Well, when we train neural networks, we check if it is OK, close enough to the result. So we always check such an absolute value. So but what we need to remember, that we cannot measure less than the spacing between consecutive floating point representations. We cannot go inside. So this is on the right hand side, we use this machine epsilon value, which I just mentioned, and maximum of this value. So if this is true, this condition, we are close enough. We cannot, well, we are just in the one group of values. And the second thing, we always divide floats by floats. So we all knew that don't divide by 0. But this is not enough. Don't divide by too small value. So what we can do, if we need to compute correctly the result C, and we have A through B, so either in our domain, we can say, OK, my values in the dividend won't be larger by A max, because I know I'm computing something. There are some financial things, or neural networks, or image processing, or whatever. Then I can compute B, what is acceptable B. B must be greater than this A max by K max value, which I can read out from this numerical limit library. Or I can go the normal way, well, normal, I mean the most popular way. If I can say, OK, my divisor won't be 0, but this is not enough. My divisor must be larger by B mean. Then A must be less than this B mean times K max. So we can read them out from this numeric limits template below here. So these are just why is that? As I mentioned, this is on my web page, in the book, in the presentation. So, but these are just OK. So we are done with the standard. Maybe too long, but that's OK. And the quest for 16-bit, quite fast. This is just OK. Realize that we need 16 bits because we need to pack values. And usually we don't, in many domains, we don't need such a precision, but we need to put all data, big data, into the memory. So why we need binary 16? So we can make it smaller. There are many custom versions. You can look them up on the net. So this is the situations like before IEEE 754 standard. The big companies are devising because of lack of the standard. But also there is this quest for adding to the standard 16-bit. So maybe it will be short float. Yes, so it was proposed in 2016, but I don't know if there are works on this or not. And there are many approaches here. Well, you can quite easily look them up from here, or just Google them. But what I found interesting, just first shot to try on, is half library. And here is my example. Hash include this half. This is a header-only library, and you can compute, for example, area of circle of something, and you can even try to. Yes, we finally have constants in C++20, so we can try to do this with PV half, but well, it might not compile yet. So here is the way around. We can call arcus cosinus on this. And here is a simple function I wrote, which is a template function. You can read all the values, all the parameters of these floats or other numerical values from the limits library. And once you call it, you can put the template whatever you wish, and you can read epsilon, radix, digits, min, max. Either it has the normalize or not, and so on. So when I use this function, we have this results. So what is interesting to see here is this epsilon value. So this is the minimum spacing, once again from 1, not from 0, from 1 to the nearest larger value, and some rounding style and so on. So we always, when doing computations, we need to write code which automatically checks if dynamics and the range of our used values is the same on the same platform, because it can be different implementation of on some platforms. So we can read this just using this FP limits or just limits library. Okay, especially if we are going, for example, for long double or things like this. So here are some information about this library. Just check it out. Is good, but it is slow because this is no hardware support. So that's the problem with all things like this. Alternatives, we have NVIDIA, FlexFloat, bfloat by Google, Intel, well. But it is usually worthy considering if you are doing massive computations, maybe my data can be 16-bit long. And you can save a lot because in many computations like neural networks, image processing, we don't need more. Well, in many cases we need, but so you can use also fixed point arithmetic in some cases. But, well, a lot of research into deep learning, especially on the edge platforms, FPGA, so we need really to squeeze data. And to squeeze data, we can use the library. This is some cool stuff, floating point compression, another library, another possibility. You can try compression on every format, but here is the library for IEEE 754, and I found useful two libraries, ZFP, proposed by Peter Lindström, in his work from 2014, fixed rate compressed floating point arrays. And from the very beginning, I can state we are using this library and we love this library because it is specialized for floating point. If you do zip or some other compression, you won't get good results because they are not optimized for this type of data. And this is optimized for floating point representations. So their main observation was that multidimensional data, tensors, images, so on, elements tend to cluster in subcubes. So what I mean is that if you take a closing pixels, for example, they probably will have similar values, except they are on the edge of something, of the image, if you are looking just at images. So they use this feature in this compression. So the more structured, like a tensor, like a multi-dimensional cube your data is, and the more similarities you have, you will gain from this library. Or for example, for visualization. So for example, if we are processing multispectral data, so it is not RGB, we have this RGGGGBB, more and more spectra. So we have cubes like this of data. So in such a cases, usually the small cubes tend to have similar values to some extent. Okay, so what's the idea? Near lossless compression scheme is proposed. So it maps small blocks of 4 to the power of d, where d is dimension, to a fixed number of bits per block defined by the user. So this is the virtue of experiments. We need to experiment. In this 3D case, this is, for example, 4 by 4 by 4 cubes. Each such a block is stored using the same user-defined number of bits. And each block is compressed in 5 steps. So align block values to a common exponent. So this is the idea. If they are similar, they have common exponents, so we can take the exponent out, just store the data, and we can save on this. So convert floating point number to a fixed point representation, run orthogonal block transformation to decorrelate the values just for better compression, like in JPEG we are doing the same, order the transform coefficients by the magnitude, and encode the coefficients 1 bit plane at a time. And this ZFP allows for random read and write access to compress FP data. If you know how the JPEG compression works, it is similar to these points. If you need more details to understand, the paper is great just to read, but you can try from experiments. In a moment, I will show you some code. So What is the characteristic? It is a C++ wrapper to the compressed Ri primitive. To the user, the vector, for example, appears the same. Cache to optimize the frequency of compression and the compression, but it is internal cache, not the processor cache, it is cache of the library. And ZFP is strongly limited to regular data. So if you supply the library with random data, don't expect too much, or you can expect even worse results. Applications, well, I already mentioned in computer graphics, machine learning, and so on. And nice license. So there are 5 compression modes: expert, fixed rate, fixed precision, fixed accuracy, reversible, lossless. Well, if you really need to have that, but you can still try to find these common exponents and have some compression. Better in this case 5 than I would say using simple zip library. And it works in parallel. And it has different APIs for C compressed arrays, and the code will be the best in a moment. Yeah, some parameters like this, but the most important is that we can use in like here. Look at this. We have this vector. We use this Mersenne twister random engine here. Uniform real distribution. We generate some values here. So once we are done with this, we define these parameters for this library to work. Here we define bits per value to store in compressed representation. So we have coarse rows, and this is the parameter of compression, so you can play with this rate. And we have this array 2D, my ZFP array, and I can do this. Okay, it has the same number of elements, but what we expect, I can copy it, and what I expect, it will be compressed, but at what price? So to find out the price, transform reduce is a nice function because it can work in parallel. So we start from begin end, and we have to supply 2 lambdas for 2 operations of adding the values, of just computing differences, square differences, and adding the values. So this is how transform reduce works. So we have this fork and join part of operations. So once we run this, we can ask for the number of bytes in this compressed data. Okay, we are done with this, and now we can print out the results, just simple things. So we see just compressing this, as I mentioned, these are random values. So I don't expect to good results, but anyway, I have this compression ratio quite large, and this mean square error of 0.63. Well, it depends on the application. If you are doing some financial things, well, maybe it is big value of 0.63 of euro difference in your bank or not. I don't know. So you always to be very careful with this. Yeah. So you have to measure. But if you are doing visualization of your data, that's perfect. No one will notice if the pixel is different by 0.63. Okay, so this is what we have. And we have another library, SZ. You can try it out as well. But we found easier to use this ZFP in many cases. Alternatives, well, what we are doing in our, let's say, research stuff is just processing tensors. So I wrote a book 10 years ago about this. So what we can do, if we have a tensor, we can do the composition of a tensor, and the composition is already compression of value. So what we did more, we did this ZFP and this already compressed, decomposed representation. So we can gain a lot. And now the almost last big thing, but really big, is POSIT representation. So we had standard floating point, we had 16-bit addendum, we had compression, and now we have quite new realm, domain of new representation. This is not IEEE standard, this is POSIT. It grew up from many research attempts, and you can find in literature, I will provide you in a moment. So what is POSIT? It's just trying to fill the gap, especially of this waste of bits and limits. Well, one thing you will see in a moment, what it fixes is it refrains from the same number of bits per exponent. The number of bits of exponent can be larger or lower. So this is the key point. But there are many, many, many details. You can find them in this paper from 2017. Gustafsson is the main author, and Yonemoto, co-author of this paper. So what we expect, larger dynamic range due to variable length and coding of exponent. And this idea comes from Golomb Price works 40 years ago, 30 years ago. More fraction bits if small exponent is sufficient. So we can trade off the number of bits for exponent with the number of bits for a fraction, because we have fixed computer word, for example, 32 bits, but we can change. We cannot adjust this in IEEE representation with double float. You have 8 bits and that's all. You don't need them. You need more precision. No way. You have to change to long double and waste more space, more memory. Never overflow to infinity or underflow, the so-called tempered arithmetic. Not a number indicates an action instead of bit pattern, but there is modification in the libraries I will show you. We have this, not a number, because it is useful. Because this POSIT is designed for easy replacement of IEEE because standard. Because otherwise, there would be a revolution, so we need to rewrite everything. No way. So if it is a replacement, if it can go just one-for-one for IEEE representation, that would be the goal. So this is more or less in this direction, but as far I don't recall any processor commercially available with POSITs. We have a lot of scientific work, FPGAs with POSITs. We also tried this in our labs, but no, not so popular yet. POSIT environments mandate the fused operations. So the fused operations are briefly, not going into details, the operations which guarantee the correct rounding of, for example, adding the values. And only the result is rounded. Okay, so once again, this image. So this is what we have in standard up and what we have in POSIT. There is new thing. We split the qubits of exponent into so-called regime bits and exponent bits. And they can be defined and adjusted. You will see in a moment. So they go here, and here is the whole story. So exponent can be variable length, and significant can be variable length. So if we don't exponent, we can have more bits for mantissa. If we need more for exponent. Regime is fixed, and you will see in a moment its role. It is just another multiplication factor. So well, certainly we have to be aware of the value. So these exponents are called ES bits in all publications on POSIT, so I use this. So here is, once again, the old thing, IEEE 754. The formula is like this. If we go to the POSIT formula, it is not much different. The difference is here in this rectangle. So we have U seed value to the power of k times 2 base to the power of e. So this is what they changed. So the two things, variable number of bits. So okay, the word is fixed. For example, 64 bits or 32 bits or 16. But we can exchange the number of ES bits with precision. Regime is still the same, and this is in a little bit different realization. Still, we have this representation with 1 here, but you will see in a moment that we can quite easily go with this tempered arithmetic, avoiding these subnumerals, which are the problematic in old standard. And here the mantissa is computed in the normal way, so we can have this. So this is the POSIT, how it works. And, well, here is a complete POSIT value. Well, from the paper of Gustafsson, because the libraries are a little bit modified. So we have these representations. The thing is, we don't lose bits. The sign bit is 0 for positive number, 1 for negative number. And what is important, if negative value, we take 2's complement. So this is not like IEEE sign magnitude, but this is 2 complement before coding the regime, exponent, and significant fraction. So we have 1, 0. And now, how these regime bits work. This is used only here to compute this UC to power of k. So how do we know k and UC it? There are a couple of rules. So we analyze only these regime bits now, which are fixed. You remember, ES is changing. This is it. A stream of zeros or ones is terminated either when the next bit is opposite or the end of the string is reached. So if we go like this, if bits are 0, then k is minus 1. So we have, for example, 1, 2, 3, 4, 0, so this is minus 4. But if we have 1, 2, 3, and the transition to 1, then it's minus 3, and so on. If they are 1, there is m minus 1. Yes? So we have, for example, 1 and 1, then it's minus 1, so we have 1 value. K is 1. And the regime indicates a scale factor. So this is the key idea, okay, the variable length and the scaling. So I can divide or multiply the whole thing by bigger or smaller number. This way I can have fractionals of bigger values. And UC is computed from this k, and this is computed like 2 to power of 2 to ES. So UC is computed from ES bits, but then we have also this k parameter. So more parameters and this variable length. So you see here if ES exponent is 0, 1, 2, so we have from this formula and taking UC 2, so we have even this UC can be 6500 for ES 4. We will have some examples in a moment. So exponent is regarded an unsigned integer. There is no bias like in old standard. There can be up to ES exponent bits. A tapered accuracy, I already mentioned, number near 1 in magnitude have more accuracy than extremely large one, extremely small numbers. If there are any bits remaining after the regime and the exponent bit, they represent the fraction mantissa. So there are no subnormal. So we'll see some examples here. If we take only 3 bits, nothing more for a POSIT, we have such a value, positive value. So this is UC this to power to 3 is 8. Usually we represent the values on the horizontal line, but well, just recalling the formula for like a helper. The better is to represent them on the circle. So you see here for K1 we have UC, for K0 we have 1, and for K minus 1 we have 1 divided by UC. So this way we can have either fractionals or larger values in the uniform way. And if we go with larger values, there are some rules. I don't want to go into some details. If you need them, you can read the paper, but well, there are different rules of just adding bits to precision and what will be the new value, So adding 1 creates a new value between 2 points on the circle, and we have some interpolation rules. One is that the value is mean position divided by UC. If the value is between other values and different more than 1, then geometric mean is computed from these values. And for midway between closest neighbors values, arithmetic mean is computed. Why is that? it is in the paper. We don't go into some mathematical details, but this is how it works. So if we are adding here the values, for example, we have 1 and 16, and we are adding in the middle value, we are adding 1 to the end, then we have this geometrical mean, which is 1 multiplied by 16, and then square root, we have 4. And the same for fractionals. So this is, if we add more, we have, having these rules, they prove that they fill this space as needed. So we have 3 bits, like in the previous example, 4 bits or 5 bits. So we can go with the precision up to the limit of our word. So here is the example. If we have such a value, sign, regime, exponent, fraction, how we compute it? Well, it is this value of UC to -3 because of this -3, because we have 3 zeros and transition to 1. Then we have exponent 2 to the power of 2, and this black is this fractional. So despite having 1 bit in front of this hidden bit, we have quite small fractional without the normals, thanks to this scaling by UC in the front. So here is the summary of POSITs. So we see that variable length. So we have many gains. So actually, it is a game winner. So hopefully, we'll be using this POSIT soon. Well, in other words, I cannot put some advantages of using IEEE 754 over POSITs, except they are not implemented in hardware yet. And some software implementations, you can Google up them, but what I use is the CPP POSIT, which is quite useful for me and for deep networks we are using. And here you can find the library, CPP POSIT, and here is the example. You can include the POSIT, make POSIT 12 bits. Well, remember, the entire talk is about saving bits. So here we have not 16 even. We have 12 bits, and we can do a lot of computations like this. But remember, OK, we can multiply them. We can convert to float to compute the values. We can compute area of a circle. But please remember of this. Well, we have large compression, but we lose some accuracy. So we always must control dynamic and precision in our computations. Certainly, just if we have 32 floats and we substitute them with POSITs, 32 bits, we expect much better results. And this is proved in the papers, so I don't go. And you can read about values of these POSITs and the future now, because time is short. So just matrix multiplication, just 2 by 2 matrices, simple thing. We teach this in a grammar school, maybe? Well, maybe not. OK. But it is quite simple. Well, if we make such a notation, it is like this. Well, if we write down all the elements, we have these factors and terms. So we see 1, 2, 3, 4, 8 multiplications. So simple is like this. So this is also what we teach when we start programming, maybe at the universities. So people do multiply matrices. And for 50 years, I'm a little bit older than this algorithm, but we avoided 1 multiplication. Well, only 1 multiplication? Well, do we care? It is more complicated. So why a single multiplication matters? Because this A11, A2, B11 can be another matrices. So this can be recursive matrix multiplication. So if you do this and you multiply huge matrices, So you avoid one, maybe not that huge multiplication, but matrix multiplication. So it really counts. And for years, it was said, no better way. It was proved that this is optimal value. But really, can we do better? And look at this. Yes, we can. Just a month ago, Nature, you can download it for free. Discovering faster matrix multiplication algorithms with reinforcement learning. So this is the future, probably. So what they did, they took alpha tensor, the one reinforcement deep learning machinery which played chess and Go and won with every human being, with the masters of Go, of chess, and they transform matrix multiplication to tensor decompositions, this into single player game agent, training alpha tensor to find efficient ways to win this game, and this way they obtained. So what they did is such a network, so this is reinforcement learning. Gradually it improved by playing the game with itself, with some guides, so it was well, again, neural network. It just was trained on the played game and synthetic demonstrations. It took an input tensor and output this decomposition of a tensor, updated the model. Here the actors, just neural network using Monte Carlo tree search game. The game was played and put again to the network. And after a couple of days or weeks, they discovered new winner. Well, 2 by 2 is already proved by Strassen that this is 7. But for 4 by 4, no one found before. So we have new world record. Yeah, just 1 month old. So probably we are not, well, we are programmers, researchers, but machines will do development for us. So AI will play a fundamental role in the field of algorithm discovery, probably. Not only to improve the existing ones, but also to discover the new ones. And maybe discover better implementations. So we programmers, coders, will not be needed anymore. We'll see. Maybe not. Maybe not. OK, so conclusions. Well, literature is big literature. You can use Wikipedia for all these things quite easily. Float formats, other things. You can have these calculators or ask students to program them. And yeah. And this is the seminal work by Donald Nutt. Well, some good papers by, and here is the seminal work about POSITs, Gustafsson. Yeah. Another things about code words, Elias. The work by Gustafsson is based on works of 1975, Elias, yes. Goldberg is quite useful tutorial on floating points. Well, new algorithm 908 to exact summation of floating point values quite fast. And we have more. We have some libraries. We have this fixed rate compression arrays in the paper. We have some papers of us, so you can Google us up. And there is this book in a moment, Discovering Faster Matrix Multiplication. This is 2022, just very fresh, reinforcement learning. So, conclusions. Yes, that's good we have the old standards. We are indebted to the founders of it, but the entire modern numerical world depends on it, but we can do more. But we must always control dynamics and precision of the numbers, whatever we are using, because we are always in the approximation world when we are doing computation. New technologies launch new demands on the data representation. Machine learning, data transfer constitutes a bottleneck in a lot of domains, yes. New directions, data compression, new formats, but mostly POSITs I would recommend. New hardware we need quite badly. I count on this RISC V or 5 implementations. This is new standard for making processors open standard. And we are still ahead of having new formats. So maybe we can use reinforcement learning to discover some better formats, I don't know. And artificial intelligence, so that's cool stuff. That's really something, if someone is asking me what is artificial intelligence, that's it. No just, detection of faces, neural networks, okay. But if something is really new from us humans, researchers, this is that. So that's all. I hope we have some time for questions. And by the way, this is the new book for teaching C++, but also with power programming, with POSITs, maybe not, but with all computations in arithmetics, in fixed point, floating point. So just please use the code. Yeah.
My question would be, if I got it right, if we now keep the same precision of the floats, we can represent, or we can do our computations with POSITs with better precision, but we trade it off with being slower, right? Because the hardware does not support it in general. Is that correct?
Yes, exactly.
Or we can keep the same precision that we have, but with less bits. So we trade. So in a way, it's a space-time trade-off.
But this is implementation issue. So once someone makes a processor with POSIT, it is a little bit harder to make hardware implementation of POSIT, but it is possible. It is proved in the FPGA. It is for years. We have FPGA platforms with POSITs working. So this is for a company. Probably there is no pressure in the market just to change it, because if something is working, we are flying to the moon and then farther. But we can really change how we compute and how we save the space, just saving on bits.
And the small follow-up question is this already a thing in like these tensor processing units, these TPUs that, for example, are used for TensorFlow? They are also using a reduced floating point format? Yes. Is this?
Good question. They implement usually their own limited precision computation. Okay. So always you exchange, for example, OpenMP have very nice ability to download some computation, some task onto GPUs. Please remember they use lower precision on GPU, so the result can be burdened by more rounding errors.
Mm-hmm. Thanks.
Thank you for the talk. It was very inspiring. I'm actually curious about similar as previous question about hardware support for POSIT. Mm-hmm. I'm aware that we will for a long time not have any real hardware, especially on consumer devices and browsers. But I'm curious about, have you explored or even tried to implement a library that would basically just use POSIT for data storage, but then use vectorized instructions and SIMD to convert data from the storage into something that is compatible with today's CPUs, perform the computation, while keeping everything either in cache or in registers, and then efficiently return data back into the POSIT format and store it into a global memory.
This is still ahead of us. So we are just starting some tensor decompositions, and well, our group of FPGA enthusiasts at the university, they plan to use POSITs finally. But the beginning implementations are using ready floating point cores with some limits. But this is the general, your direction, actually. We need to go this direction. I hope it will be faster, especially all this NVIDIA and all this. Well, I know that they already did a lot of research on changing precision of value, because when you train the neural networks offline on big machines, then you download it to the GPUs. So you need to convert to 16 bits and don't lose the operation of the machinery. So if you Google up and NVIDIA especially, they did a lot of libraries for converting values and training networks. And I know that they are working on POSITs. If they have something ready, I don't know, but I would expect something quite fast because...
Yeah, I agree on that term for training on some, in some data centers on big machines, but from your talk, I actually got an impression that the best use of POSITs would be on a tiny devices on, for example, machine learning inference in WebAssembly, in web browser, or on small Android or RS devices, which will definitely not have hardware support for POSIT for a very long time.
Well, I'm a little bit older probably. I remember working on embedded systems not having floating point at all. So probably some of you remember these times, but they changed quite fast, and all processors now have not only coprocessors, floating point coprocessor, external devices, but even each core has embedded. So this is progressing quite fast, like with this RISC V or 5 technology. I'm sure that at many universities there are works. So this is the only question if the mainstream will catch it. Yeah. I hope it will. But one more thing, we can use it, we can play it, and we can have the two versions, for example. And well, once we have hardware, we can use our more optimal version for that hardware.
Thank you.
Thank you.